Welcome back, everybody, to another episode of BIO259, where we dive into the fascinating world of skin and connective tissues. It's week 5, and oh boy, do we have a lot to cover today. Now, before we get into the nitty-gritty of anatomy, a quick reminder to all you students out there. The upcoming lab practical's around the corner, but don't stress too much because we've got you covered. Dr. Rosario posted an incredible walkthrough video from last semester that should really help with your prep.
Yeah, and can I just say, this video is a great visual explanation of some of the structures you'll need to know for the exam, so take a look at it. Maybe watch it twice.
And also,
Yes. And also, big thanks to all the students who submitted captions for Sophie's picture we posted. Honestly, some of those captions had me cracking up during office hours.
who doesn't love a little Sophie moment, right? All right, so today's episode is packed. Stay tuned as we dissect, pun intended, the layers of the skin and much, much more. All right, Dr. Rosario, after all the laughs about Sophie, let's get serious and peel back the layers. Literally. Where better to start than with the skin itself?
Hahaha, yes, let's jump right into this. I mean, the skin is fascinating, right? It's the largest organ we have, and it's not just a single layer. It's got 3 main regions, the epidermis, the dermis, and the hypodermis. Think of it like building a house.
Wait, a house.
Exactly, a house. The epidermis, the very top layer, is like the shingles on the roof. It's there to protect everything underneath. Beneath that, you've got the dermis, which is like your support beams giving structure and strength. And then way down in the hypodermis, that's like the foundation. It's where we store a lot of fat that literally cushions and supports everything else.
Okay, now that's a super visual way to break it down. So, within the epidermis, since it sits on top, how does it do its job of protecting us so well?
Great question. The epidermis itself has 5 layers, each playing a specific role. Picture them as a production line. It starts with the stratum basal at the base. That's where new skin cells are born. These cells eventually get pushed upward, layer by layer, until they reach the surface. By the time they make it to the top, in the stratum corneum, they're essentially little flaky shields packed with keratin, a protein that makes them tough as nails. Literally, keratin is also what's in your nails.
I can't believe those cells are dead by the time they're on the surface. And aren't we constantly shedding them too?
Oh, absolutely. You're shedding an estimated 40 pounds of skin in your lifetime. Just imagine that. All those flakes contribute to the dust you vacuum at home.
Wait, stop. Household dust is partly made of dead skin cells?
Yup. Mind blown, right? It's one of those but cool facts. And the cool part is it isn't random. Those layers act like an assembly line, constantly renewing and repairing. And fun fact, if you've got dandruff, that's just your scalp shedding its stratum corneum faster than usual.
Okay, that's fascinating. And a little gross. But you said earlier that melanin is made in the bottom layer, right? What's its job?
Oh, melanin is incredible. It's produced by melanocytes in the stratum basal, and it gives our skin its color. More importantly, though, it protects us by soaking up UV radiation. It's like your skin's natural sunscreen, shielding those deeper layers from harmful rays that could damage our DNA.
That explains why people with fairer skin burn easier, right?
Exactly. Less melanin means less natural protection from UV exposure. But here's something cool. Have you ever thought about why calluses form only on certain parts of your skin?
I mean, yeah, but is it tied to the layers?
It is. When there's consistent pressure or friction, your skin actually thickens its uppermost layer, the stratum corneum, making it tougher. It's like your body saying, hey, let's armor up where we need extra protection.
Wow, that's so efficient. Your body is basically its own adaptive architect.
Exactly. And there's more, but I could geek out about this all day. I'll just leave you with this. Every part of your skin is designed to work as a team. The dead upper layers, the pigment-producing melanocytes, even the protective oils secreted by your glands. It's like a well-oiled and keratin-filled machine.
Speaking of oiled machines, we'll get into another fascinating part of our body next, connective tissue and the incredible extracellular matrix. Stay tuned. So, as we've seen, the skin is like the ultimate architectural shield, adapting and protecting us. But every great structure needs a strong framework, right? That's where connective tissues come in. Dr. Rosario, I've got to ask, how does it all hold together?
Oh, absolutely. People don't realize how much connective tissue does. It's basically the unsung hero of our bodies. If skin is the protective barrier, then connective tissue is the complex infrastructure supporting everything from our bones to our blood vessels. And at the heart of it all is the extracellular matrix.
Okay, so the extracellular matrix. I know you've mentioned it in your lectures, it's the space outside the cells, but what exactly is it doing there?
Great question. The extracellular matrix, or ECM, is essentially this intricate network of fibers and ground substance that provides both structure and support. Think of it as scaffolding, giving our tissues their shape and, honestly, their resilience.
Scaffolding? I like that. But these fibers are all different, right?
Exactly. There are three main types of fibers to know: collagen, elastic, and reticular. Each one has a unique job. Collagen fibers are like thick, super strong ropes. They give connective tissues their tensile strength, meaning they can withstand being pulled or stretched without breaking. Picture the ropes of a suspension bridge. That's collagen in action in things like your tendons.
All right, so collagen is the workhorse. What about elastic fibers?
Elastic fibers are like rubber bands. They stretch and then snap back into place. They're why tissues like your skin and the cartilage in your ear are flexible yet springy. Without these fibers, our tissues would be rigid and unable to bounce back after being stretched. Ever fold your ear and let go? That's elastic fibers doing their thing.
Okay, so we've got ropes and rubber bands. What about reticular fibers? Where do they fit into the picture?
Reticular fibers are more like a safety net or spider web. They're thin, delicate, and act as a support framework for cells, particularly in soft tissues like your spleen or bone marrow. They add structure without bulk. Think of them as a lattice for other cells to cling to.
I like how each type plays its role. But these fibers can't build themselves, right?
Correct. Enter the fibroblasts. These are the master builders of connective tissue. Fibroblasts produce the fibers and matrix components, and depending on the tissue they're in, they get specialized names. In cartilage, they're called chondroblasts. In bone, they become osteoblasts.
Speaking of specialization, I remember pulling a tendon years ago while running. And let me tell you, it felt like it would never heal. Is that because tendons have poor blood supply?
Bingo! Tendons are made up almost entirely of densely packed collagen fibers with very few cells and limited blood vessels. That's why healing takes so long. The few cells there have to do all the repairing, and without a steady blood flow, nutrients and oxygen trickle in pretty slowly. It's like trying to fuel an entire race car with one tiny gas pump.
Ouch, makes sense now. But not everything in connective tissue is so slow on the uptake. I hear adipose tissue is quite the multitasker.
Oh, totally. Adipose tissue, or fat tissue, is like the body's power bank. It's highly vascularized because your body needs to access that stored energy quickly when needed. Each fat cell acts as an efficient reservoir of lipids, packing a lot of energy into a small space. It's like having snacks stored in every drawer, ready to be grabbed in a pinch.
Ha ha ha. Snacks in every drawer. I love it. So adipose tissue is energy storage, but poor blood supply slows down things like tendons. It's like connective tissue is either feast or famine when it comes to vascularization.
Exactly. And each type of connective tissue is perfectly tailored to do what it needs, whether that's cushioning organs, transmitting mechanical forces, or acting as an energy reserve.
You know, hearing all of this, I'm realizing how easy it is to take these tissues for granted. They're literally holding us together and keeping us running. It's impressive.
It really is, and honestly, without connective tissue, we'd just be a pile of squishy cells. No structure, no movement. It's no wonder this system is so vital to our survival and function.
Well, Dr. Rosario, this has been an eye-opening discussion today. From scaffolding and rubber bands to energy snacks and stubborn tendons, I feel like I'll never look at my body's inner workings the same way again.
My job is done then. It's been a blast geeking out about connective tissues with you all. To everyone listening, I hope this makes you appreciate the hidden complexity of what keeps your body ticking.
Absolutely. And with that, we're wrapping up this week's episode of BIO259. Thanks for joining us on this deep dive into skin and connective tissue. Take good care of yourself, And we'll see you next time for another fascinating journey through biology. Take care.